panel joint stress failures are a classic example of defects that originate from vehicle structure rather than coating formulation alone. Welds, rivets, spot joint seams, and bonded joints introduce localized stiffness changes, residual stress, and geometric discontinuities that place extraordinary strain on the coating system throughout the vehicle's life. From an OEM perspective, these failures are expected risk zones that must be engineered, not eliminated. At every panel join, the substrate behavior changes abruptly. Weld nuggets create hard, stiff points surrounded by heat-affected zones with altered metallurgy. Rivets and mechanical fasteners introduce point loads and clamp forces. Adhesive bonded joints cure and shrink differently from surrounding metal. When the vehicle experiences vibration, body flex, or thermal cycling, these areas do not move uniformly, and the coating is forced to bridge incompatible movements. Residual stress is introduced even before the vehicle leaves the plant. Welding locally heats the substrate, followed by rapid cooling, which locks in tensile and compressive stresses. When coatings are applied and cured, additional shrinkage stress is superimposed on an already stressed substrate. The coating appears intact initially, but it is preloaded with hidden strain that only requires service exposure to activate failure. Film build variation is common at joins. Spray patterns struggle to coat recesses around welds and rivet heads uniformly, resulting in thin films at the most stressed locations. Conversely, material accumulation around protrusions can lead to excessive thickness and increased brittleness. Both conditions promote crack initiation under cyclic loading. Cross-link density strongly influences join durability. Highly cross-linked coatings resist chemical attack, but lack the elongation needed to tolerate repeated micromovement. Lower cross-link density systems flex better, but may fatigue over time, leading to gradual loss of adhesion. OEM formulations target a balance, where the coating can deform elastically under service loads without accumulating permanent damage. Primers play a disproportionately important role at panel joins. Flexible primers help distribute strain and reduce stress concentration at the interface between substrate and decorative layers. Without adequate primer compliance, stress transfers directly to the base coat and clear coat, causing cracking, crazing, or adhesion loss along seam lines. Additives contribute indirectly. Stress relief additives reduce residual shrinkage during cure, lowering initial strain. Flow and leveling additives help smooth transitions around welds and fasteners, minimizing geometric stress concentrators. However, additives cannot compensate for poor weld geometry, sharp edges, or inadequate film coverage. Environmental exposure accelerates joint failures. Moisture, salts, and contaminants preferentially accumulate along seams and joins. Once microcracks form, these agents penetrate beneath the coating, promoting corrosion and undermining adhesion. This explains why seam failures often evolve into corrosion creep, even when flat panels remain intact. Thermal cycling is particularly damaging. Different materials at joins, steel to aluminum, metal to adhesive, metal to plastic, expand at different rates. Each temperature cycle induces shear stress at the coating, substrate interface. Over thousands of cycles, fatigue damage accumulates, eventually manifesting as cracking, delamination, or blistering localized to joints. Detection of panel joint stress failures requires careful inspection. Linear cracks following weld lines, circular cracking around rivets, or localized delamination near bonded seams indicate strain-driven mechanisms. Accelerated durability tests combine vibration, thermal cycling, and humidity exposure to reproduce these failures before field release. From a troubleshooting standpoint, engineers evaluate weld quality, edge radii, film build uniformity, primer flexibility, and cure balance. Solutions may include smoothing weld profiles, increasing primer thickness locally, adjusting bake schedules, or modifying joint design to reduce stiffness mismatch. Repainting without addressing the underlying stress source rarely provides lasting improvement. Panel joint stress failures demonstrate that coatings are structural participants, not passive layers. They must accommodate movement, absorb strain, and maintain adhesion across complex interfaces for years. OEM durability success depends on aligning coating chemistry, application process, and body design to manage stress where it is most concentrated. If you've observed cracking, peeling, or corrosion tracing weld lines, rivets, or seams, leave your questions in the comments. In the next episode, we'll continue with fatigue-driven coating failures caused by repeated door and closure movement, further expanding this stress mechanics theme.